tutorials for this particular chapter which we just completed. I will try to give you an overview of how we will organize these tutorials. Each tutorial session will essentially be like related to problem solving, and the problem solving will be related to the concepts that have been discussed in the theoretical description. So for this particular chapter, the important concepts on which we will be having problem solving will be viscosity, surface tension and compressibility. And there will be total 6 problems, and we have 3 teaching assistants. I request them to come here and I will introduce all of them to you. And these 3 teaching assistants will be there throughout this particular program, and for all the tutorials essentially they will be helping out to helping you to work out the problem. He is Dr. Sukumar Poti, who has completed his PhD under the guidance of Professor Som and me. So he has very recently completed, and he also has vast teaching experience by himself. And the other 2 teaching assistants is Uddipto Ghosh and he is Aditya Bandyopadhyay. Both of them are PhD students working with me, and they have prior to that completed their BTech and dual degree program at IIT Kharagpur itself. So these 3 are our teaching assistants, and they are just brilliant people. So in many cases you will find that they will be of more help to you than most of us, and the way in which the tutorial sessions will be organized is like this. Each of them will come and introduce the problem. The problems have been designed by all teachers and tutors combined together. So we have put all our thought in like identifying that what could be ideal problems to work with in the coordinators workshop. So they will first introduce the problems, and then they will work together with you to solve the problems. Not that they will just dictate you the solution. Of course they will help you out with the solution. So each of them will stand here and like go through the problem, and the remaining 2 tutors will be there walking around you. So they will not be sitting here. One of the tutors will be standing here and will be discussing about the problem here itself on the dais, but off the dais there will be 2 tutors who will be roaming around and looking into the difficulties that you might face for addressing the problem. In addition to that, me and Professor Som will also be present to discuss with you on the problem. So that is how we will be organizing the first tutorial. So I will invite Uddipto to like go through the first problem.
Hello. Move towards the tutorials. The first problem, if you please. So the first problem goes like this. I'll first read the problem. There is a diagram which goes with this problem. The diagram is given in the next page. We'll move on to that, but first we will read the problem. The problem goes like this. A block of mass m slides on a thin film of oil. The film thickness is h and the area of the block is a. When released, mass m exerts tension on the cord, causing the block to accelerate. Neglect friction in the pulley and air resistance. Develop an algebraic expression for the viscous force that acts on the block when it moves at speed v. Derive a differential equation for the block speed as a function of time. So that is the problem. It's a pretty simple problem. So here is the diagram for the problem. So this is the block. So this is the block. and the oil film is also clear here, and this is the pulley, and the gravity acts in this direction, that is the vertical direction, and the axis system, the XY axis have been shown in the figure here at the top corner. So we have two bodies here, two separate bodies. The free body diagram for these two bodies have been shown also. So the oil film is also shown here. So what happens here is that this mass m exerts a force on this cord, and this cord in turn exerts a force on this block, and this force is in turn this force moves causes this fluid to move. Now now this fluid has some viscosity, and that is why this fluid will exert some viscous forces on this block. So overall, it will be a balance between this viscous force and the tension of this cord for this block, and for this block it will be a balance between the tension in the cord and the gravity. So first what we do is we write the shear stress in the fluid. The shear stress is given by this. I'm sorry, this tau is mixed up. So it will be, this is tau, and more precisely this is actually tau yx for the fluid. So this is tau, and this is simply follows the Newton's laws of viscosity. Mu times du dy. Mu is the viscosity and u is the velocity. Du dy is the velocity gradient. Now what we do here, we assume the velocity of this oil film to be linear. So we assume that velocity varies linearly with y. So velocity is 0 at this on this solid, and is v here at the block surface. So like at the block surface. So this is simply, so this gradient then simply turns out to be v block by h. H is the film thickness, and v block is the velocity of the block. So this is the stress, that is the force per unit area. So the total force on the block will be simply this stress times the area. So the stress is mu times v by h, v block by h. That times area is the force. So now we can write an equation of motion for the block, which is simply Newton's laws of motion for the block. This is the mass times acceleration of the block is net force acting on the block. As I said, this is tension of the cord minus the viscous force. And for the falling mass, it is again the same. And in this case, gravity will be acting, and of course, again the tension of the in the cord. So here, of course, since the cord is not stretching, the cord has a constant length. So so velocity of the falling mass and the velocity of the block will be equal, which we denote as v. So finally, we put we add equation A and equation B and replace this Vm or V block both with V. So we finally have this equation here. You can see this is the equation, final equation, which we have been asked to derive. This is the acceleration dv dt. This is actually a very simple equation to solve, but we have not been asked to solve. So that's it. Thank you.
Now coming to second problem. Yeah.
So here is the problem statement again. So problem goes like this: a block of mass m slides on a thin film of oil. So what we'll do is we'll first draw this block m and this thin film of oil. So so this is so these are actually on two different pages.
Written in words that you can write. This is the problem he will explain. That a block which is pulled by a string by this system, by use of a falling mass like that, which goes over a pulley, there is a fluid layer, liquid layer, okay, which by virtue of viscosity gives a drag, force in the opposite direction to its motion. So as a resultant of this, it moves with acceleration. If the force, net force is not zero, there will be acceleration. Now you explain. So this is the problem. So how to break that equation of motion?
So as you can see, this is the problem. So this is the block of mass m, which slides on a thin film of oil. So this is the thin film of oil. This red marked area, that is a thin film of oil. So this block of mass m, capital M, slides on this thin film, and this is attached. This film of thickness is of course of thickness h, as given here, and this block has an area. So area of this portion of the block, this area is A. It's given. So this block, as you can see, is attached to another block of mass m. This is a block of mass small m. So this is attached to this small block with a string and a pulley system. So this is a pulley and the string, and gravity is of course acting in the vertically downward direction, this direction, as mentioned here. So when this system is released, initially at rest, the system was initially at rest, and when the system is released, this mass will fall down. This mass will fall down. Now this mass will fall down because of gravity. Now that will create a tension in this string, and that tension. So this tension will be acting throughout the string, and this tension will cause this block to move. Now when this block moves, the fluid here that is beneath the block will also start moving. And because this fluid starts moving, this fluid will exert a viscous force on this block. So this viscous force will this fluid will of course try to will of course try to resist the motion of this block. So the viscous force will basically act in this direction. So that is the negative x direction. So tension. So this block will be acted upon now by two forces. One along the string, which we call the tension of the string, which we denote as T, and the second force will be the viscous force of the fluid, which will be acting in the negative x direction. The oil will try to resist the motion of the block. Of course, gravity and normal force will be acting here, but those forces are not important for this block, as it's sitting firmly on this platform. For this block, however, the two forces will be, one, of course, the tension of the string. Now, due to Newton's third law of motion, this tension will be same as T, as all of us know, and the gravity will act on this block in this direction. So this is mg. So the force so if we now draw the free body diagram for this block, which is drawn here, as you can see. So this is the viscous force, as I was saying. The viscous force acting, of course, this viscous force will act at this surface because the block is in contact with the fluid and on this surface, right? So this is where the viscous force acts. So this is the viscous force acting in the negative x direction. We get the directions from this diagram here. The axis has been shown. This is the x-axis, positive x. This is the positive y-axis, and this is the tension of the string, which has been denoted as Ft here. This is same as T, and of course, gravity will act here. So this is the gravitational pull on this big block, and this is a normal force. So what happens is here, since it is sitting on this table, so this normal force N will balance gravity. So now the only unbalanced forces rather on the block are Fv and Ft. Fv is due to viscous force that comes from the oil, and Ft is the tension of the string. So viscous force is of course given by viscous stress times area. So viscous stress in the oil, that is times the area of the block. So the viscous stress in the oil is expressed as this. Since the oil is assumed to be a Newtonian fluid, it follows a linear relationship. This is the velocity gradient, So this, when this block moves, it creates a velocity in the fluid, as we have mentioned, and that creates a velocity gradient, and that times the viscosity gives us the total stress on this block. So now we have to calculate the velocity, this or rather the velocity gradient, that is the du dy, this term. So if we magnify this area where the oil film is, I'm drawing it the bottom of the page, so it will be something like so. Okay. It will be something like this. So this is the block of mass m, and this is the table. This is this bottom table, and this is block of mass m, and the oil is here. So we are only drawing a portion that is in the middle of this, somewhere here, somewhere here in the system. So if the block moves with velocity v, so the velocity of this position will be v, and since this table is not moving, that is why the velocity here will be 0. So this will be u here, and u will be 0 here, since this table is not moving. Now we will assume that the velocity varies linearly with y. So this is suppose this is we'll say this is y1 direction. So we have already noted this as y, so we will call this direction y1, and this is x direction as mentioned here. So the velocity u is 0 here, and the velocity is v here, right? So now we can say that the velocity, if we write, so u is a linear function of y, as we have assumed. If that is so, then we can write u equal to k times some k times y1, right? Since it's a linear function of this coordinate y1. Now we know that at y equal to 0, u equal to 0, because this will be satisfied because of the no slip boundary condition, as discussed earlier. So that condition is satisfied here automatically. Then we move on to this plate, where at y equal to a, so this plate's location is y equal to h, right? This height is h, as mentioned in the figure. So at y equal to h, the velocity here is v, as mentioned. So then we write kh equal to v. So from this gives us the value of k. So now we know k equal to v by h. So what we do is here in this problem, this v has been denoted as v block. So we write it as v block. So now we know this k. So now we can from this equation we know k, and we can substitute this this expression for k here, and we can calculate du dy. So this du dy will be nothing but, so du dy1, that is equal to k, that is equal to v block by h. So this is the value of the velocity gradient that we needed here. This is the velocity gradient, and that multiplied by viscosity will give us the viscous stress. So tau yx would be, so mu times du dy1. We use y1 here because we have, so y1 is the local coordinate here. So for this channel, y1 is the local coordinate here. That is why we are using y1. So this will be nothing but mu v block by h. So now the force, total force will be tau times area. Tau is the stress. Stress is the force per unit area. So it is nothing but for stress times area. Area is given for the block. A is the area of the block, as we have mentioned, as mentioned in the problem. So now we have calculated tau, which is nothing but this mu times v block by h, and that multiplied by area. So this gives us the viscous force on this block. So Fv is given. Ft we do not know. That is the tension in the string. That is an unknown. That we'll have to determine later on. So now we move on to this. Once this block is done, we move on to this second body. So for the second body, only two forces are at work. These two forces are gravity, as mentioned here. This mg working in this direction, working vertically downwards, and the surface and the tension in the string, that is Ft, denoted here by Ft. So this is a pretty simple problem for this particular block. So if we now So if we now move on to for writing the equations for the block, which will be, if we write the equation for this block, for this one, this block, this will be nothing but m times acceleration is equal to net force on the block. The net force on the block is Ft in the positive x direction, so write Ft, and Fv in the negative x direction. So this is acceleration in the x direction, this is Ax. So Ft in the positive x direction and Fv, that is the viscous force that we have calculated from here, Fv equal to this. So this will be Ft minus Fb. Now of course Ax, as we all know, Ax is simply given by dv block dt. This is the expression for acceleration. So this is the time derivative of velocity. So we replace Ax with this expression, so we get this equation. Minus Fv. So Ft here, so Fv here is known, but Ft here is unknown. So to know Ft, we apply the Newton's laws of motion to this block, the smaller block. The smaller block, we again write the same Newton's second law. So mass times acceleration. But in this case, the acceleration will be in the y direction, because this block is moving in the y direction. The vertical direction is y. This block is moving in the y direction, so it will be m ay is equal to net force. So net force is the gravity, that is mg. So this is positive because we have denoted the positive x-axis in this. So downwards, the downwards is the positive y-axis, and upwards is the negative y-axis. So since gravity is acting downwards, this force will be positive, and minus this tension in the string. So Ft. Again, we can write Ay as dv. So if we write the velocity of this block as small vm as denoted in the problem, we can write it like this. So A is nothing but dvm dt. The velocity of this block is vm. The velocity of this block we denote as v block. So we can replace this, replace Ay with this in this equation, and we finally end up with this equation B. And we have already obtained equation A for the other block, this block. So now we have two equations. So now we can add these two equations. So you will see that Ft cancels out automatically, right? We can add these two, and Ft is an unknown, so we can cancel it out very easily by adding these two equations. And we also note the fact that this string is a non-stretchable string. So this string is not stretching, it's not changing in length. That means the velocity of this block must be same as the velocity of this block. The magnitude, these two magnitudes of these velocities must be the same. But for the direction is different. This is moving in the positive x direction, and this is moving in the negative. This is moving in the positive y direction. But the magnitude of the velocity of these two velocities are, of course, same. So that we express here. So Vm is equal to v block, that we denote as a common with a common symbol, that is v. So now we add these two equations. So by adding, left hand side is simply this. This is a very simple exercise. It simply adds, and since these two are equal, this comes out. This comes out. This dv/dt comes out. Right hand side is Ft cancels. What remains is mg. Mg is here minus Fv. So Fv, as we have calculated in the previous slide, is this. So mu into v block. V block again is equal to nothing but v. So mu v by h times a. So this is Fv. So here it is nothing but mg. Right hand side is nothing but mg minus Fv. Fv is nothing but, as we have seen, this is nothing but mu v by h times a. So we replace this, we replace Fv by this, and we end up finally with this equation. So this is the final equation that we obtain for the motion of this block. This relates the acceleration of the block to the velocity of the block, as has been asked in the problem. somebody has missed it, problem.
Now coming to second problem, just first I have gone through the statement of the problem. A cylinder of radius R1 rotates concentrically inside a fixed hollow cylinder of radius R2. Both the cylinders are of length L. And our objective is to find the viscosity of the liquid which fills the space between the cylinders if a torque of T is required to maintain an angular velocity omega. So for my knowledge is concerned, most of you are familiar with this problem. So this is problem that we commonly use to measure the viscosity of fluid by using rotating cylinder viscometer. This viscometer is the device which is used to measure the viscosity, and similar type of problem we have encountered in many industrial applications. Like if we see there is a necessity to transmit power by means of a shaft which is housed by means of a lubricating oil. So I am not going into the details of that. First here our objective is just to find the viscosity of liquid which fills the space between concentric cylinder. So now if I draw the inside cylinder is rotating with an angular velocity of omega, whereas the outside cylinder remains stationary. And the space between the cylinders are filled by a liquid of unknown viscosity. Our objective is just to find the viscosity of the liquid. So you know that the fluid always offers a resistance to the rotation of the inner cylinder by means of viscosity. That means that there is a need to supply a torque to resist that viscosity. That means the torque is applied must be balanced by the resisting torque. Now our objective to find the torque, which is nothing other than the shear stress or shear force into the torque arm. Again the shear force is nothing other than the shear stress and the surface area. Now if we consider within the fluid at a radius small r, let us consider a fluid layer. This is a fluid layer. Now tell me, what is the surface area which is responsible for the shear force? Definitely this is nothing the circumference into the length of the cylinder. So here the circumference is the 2 pi r and the length of the cylinder is L. That means the surface area which is responsible for the shear force is the 2 pi r L. So now if we come to the at any axial torque, this is shear stress tau, 2 pi r L is the force surface area which is responsible for the shear force, and r, that means we can easily find the shear stress as torque by 2 pi r square L. Fine. Now next our objective is to find the shear stress, this tau. So for tau is unknown. What is the parameter that is given? Torque is given. This is given parameter. Length of the cylinder is given. So our objective to find the shear stress. So you are already familiar with the Newton's law of viscosity. So that means I already told that tau is somehow related to this shear stress is related to the rate of angular deformation, and here it is in terms of the velocity gradient. Now here, one more thing that already mentioned by Professor Chakraborty, that how to measure the y direction. Here if we measure r from the center of rotation of the inner cylinder, the y must be from the outer cylinder. That means that here if you consider r, and if we relate to r and y, this is nothing, capital R minus small y. Yes. So we can write that shear stress tau, that is nothing minus mu dphi dr. Any problem? This is tau equals to mu del v dy. Here r and y, if we write here the relation where r is measured from here and y is measured just from the outer cylinder. So we can write the shear stress, the velocity gradient, as dv dr equals to minus tau by mu. Again we have already found here the tau equals to t by 2 pi r square L. If we substitute this tau, we get dv dr equals to minus t 2 pi r square L mu. Fine. So now if we integrate this velocity gradient throughout the domain, domain means the from inner cylinder to outer cylinder, thus we get the dv v outer minus v inner. We are already mentioned v outer is the outside cylinder is stationary, that means the v outer is 0, or is the inner cylinder is just omega r1. This is, and now if we integrate this from r1 to r2, we get this expression. So now our objective to find the mu, dynamic viscosity of the liquid that fills the cylinders. If we simplify these expressions, we get this type of expression. That means that after simplification it comes T R2 minus R1 by 2 pi L omega R1 square R2. Now one important thing is that if we here del V del R equals to minus, here one thing you have seen, tau equals to minus mu dV dr. If we use a linear velocity profile, that means if the space between the cylinders is very thin, if you use the linear velocity profile, does the same expression for dynamic viscosity will come or not? That's the question. Just simply if we go through that, definitely that this will mu omega r1 by r2 minus r1. This is the shear stress. Then shear force or torque mu omega r1 r2 minus r1. This is the shear stress. What will be the surface area? 2 pi. Since the thickness of the liquid is very thin, we can simply use this is 2 pi r1L. Yes. And similarly, that's the, here we can use simply r1 or r2 since the thickness is very small. So now if we simplify this, the T r2 minus r1, 2 pi omega r1 square r2L. So if you see, the expression are totally same. Clear? Any problem to understand?
Hello. Hello. Sir, I have one question. Yes, we have not considered the fluid field between at the bottom of the inner cylinder.
Yeah.
The fluid will also in the gap at the bottom face of the inner cylinder.
Yeah, that's the rotation. It's due to the rotation of the inner cylinder.
Huh.
Yeah.
So the viscosity will also affect from the bottom side also.
Yeah, that's
Okay. Okay. That's. If it is horizontal, then it's okay.
yeah, that's not.
It is completely filled with the oil. The gap is completely filled with oil. So for small gap widths, the solution remains valid. Infinite, the tube is infinite in all in both the directions. No end effects. Okay, so the third question is, please note it down. A circular disc of radius r is kept at a small height h above a fixed bed by means of a layer of oil of dynamic viscosity mu. So this is the disc and this is the fixed bed. So the disc of radius r is kept at a height small h above the fixed bed by means of a layer of oil. So between the two plates there is oil. If the disc is rotated at an angular velocity omega, obtain an expression for the viscous torque on the disc. Assume linear variation of velocity within the oil film. So the disc is rotated with an angular velocity omega. So in 3D, this is the fixed bed. And this is rotated with an angular velocity omega. So in the plane, the velocity at any cross section r will be omega into r. This velocity is in the plane. So as r increases, the linear velocity at the circumference also increases. So at any cross section r, the velocity into the plane is omega into r. Now the gradient of velocity will be equal to the velocity at the top plate divided by minus the velocity of the bed, which is 0. The bed is assumed to be fixed. So the gradient of velocity is the velocity of the top plate is equal to omega r divided by the gap, which is equal to h. So why do we need the velocity gradient? Because we want to find out what the torque is. So the first step is obtaining the gradient of velocity, which is equal to omega into small r by h, where small r is any arbitrary r. As Professor Chakraborty had said, the stress is proportional to the gradient of velocity through the proportionality constant of the dynamic viscosity. So tau equal to mu into du dy. When we assume the profile to be linear, du dy will be simply what we had derived before, omega r divided by h. So the stress, the shear stress at the top wall is equal to mu into du dy, which is equal to mu into omega r by h. From this elemental shear stress, we can find out how much force is acting on this elemental area. So if this strip is of a width dr, the area of this strip will be 2 pi r into dr. So the stress tau acts on this elemental area, which is equal to 2 pi r into dr. As a result of that, the elemental force, the shear force acting on the top plate, can be found out as tau into dA, which is equal to this tau into the area of the elemental strip. So mu into omega r by h into 2 pi r dr. Now we are interested in finding out how much torque we have to apply. So this elemental shear force is acted upon by a moment arm r. This force at this point is acted upon by a moment arm r. Let me draw it clearly. If this is dF and this is the area of the strip, the moment will be equal to this small r times dF. So the elemental torque dt is equal to dF times r. So we plug in the value of dF as we had found out earlier as tau into dA and multiply that by r. We obtain an expression for the elemental torque. Now to find out the total torque acting on this, we simply integrate the differential torque over the domain, which is ranging from the center of the disk at r equal to 0, small r equal to 0, to the edge of the disk at small r equal to capital R. So you integrate that expression with respect to r from 0 to capital R and hence obtain an expression for the total viscous torque acting on this. So this is the expression for the total torque required to keep the disk rotating at an angular velocity omega at a height small h. This can be used to measure the viscosity and is a fundamental in the viscometers, because you can evaluate viscosity by knowing the amount of torque you are needing to rotate it and by knowing the angular velocity at which it is rotating. Okay. Any questions? So we move on to the next question. This is pertaining to surface tension. So please note it down. What is the pressure within a 1 millimeter diameter spherical droplet of water relative to the atmospheric pressure outside? So we have a droplet of water which is in an quiescent atmosphere, and is given that the diameter is 1 millimeter. So the task is to evaluate what is the differential in the pressure, how much is the delta P because of this surface tension. So from the Young-Laplace equation, we had delta P equal to sigma times 1 by R1 plus 1 by R2, where R1 and R2 were the two radii of curvatures. In the case of a spherical drop, R1 equal to R2 equal to radius of droplet. So this equation boils down to 2 sigma by R. The typical value of surface tension of water in contact with air is 0.073 Newton per meter. So on plugging in the values, 2 into sigma divided by R, we find that the pressure inside the droplet is greater than the atmosphere by 292 Newton per meter square. This is a straightforward calculation. So because of this curvature, the inside pressure exceeds that of the atmosphere by this value. Any question? Yes.
The answer is 146.
For which? This one?
Last one.
Which question? 292. 2 sigma by r. R is 0.5 mm. The diameter is 1 mm. The radius is 0.5 mm. See, it's straightforward, right? 2 into 0.073 divided by 0.5 10 raised to minus 3. So it goes up 4 into 0.070 10 raised to minus 3. It's 292. Okay. That is diameter, not the, use the diameter, I guess. Okay.
Very clear. They have been explained to you very clearly. So we move on to the next problem. Yeah. So the problem is this: find the change in volume of a 1 meter cube of water at 27 degrees Celsius when subjected to a pressure increase of 2 meganewton per meter square. The bulk modulus of elasticity of water is given at 27 degrees Celsius, and that is 2.24 into 10 to the power 9 Newton per meter square. So it's a very straightforward problem. We know that the bulk modulus is defined as Som sir earlier told us. It is simply the limit delta V tends to 0, or rather delta V star. There will be a minus sign. Delta P delta V by V. So this, as you know, is known as the volumetric strain. And this is the increase in pressure. The increase in pressure is given straightforward. It's given as 2 meganewton per meter square. That is 2 into 10 to the power 6 Newton per meter square. And we have been asked to find out delta V. We know E. So here we can find out. So here we can just remove this limit from this from this relation, and we can simply write this. So if you remove limit from this relation, you simply find this. I'm sorry. You simply find this relation. So we have been asked to find out this, and what we are given is this has been given to us as 2 into 10 to the power 6. This is mentioned as 2.24 10 to the power 9 Newton per meter square. This we can see from here. And V is also given as 1 meter cube. It is, you can see a volume of water is 1 meter cube. So V is given, delta V has been asked to find out, delta P is given, E is given. It's a very straightforward exercise. We can just put the values in and we will finally find this. So this is minus of 10 to the power minus of 8.89 10 to the power minus 3 meter cube. As you can see, this is negative. Delta V is negative, which means that which shows us that if we apply pressure, any body compresses. That is, it decreases in volume. And very strictly speaking, this compressibility, as Som sir earlier told, is the isothermal compressibility, as it's mentioned, as the temperature is mentioned. This is E, that is as at constant temperature. So, any doubts? Can I take it away?
Thus, this problem is related to whether a particular flow is incompressible or compressible. Just first go through the problem statement. Air is flowing through a tube such that the air pressures at two sections are 8 kilopascal. This is not absolute, this is gauge, and 5 kilopascal gauge, respectively, at the same temperature. It is given that the flow can be considered as incompressible if the density of the fluid changes by less than 5%. As already mentioned, that's the Mach number is less than 0.33, similar to that. Do you think that this flow could be considered as incompressible? And assume atmospheric pressure equals to 101 kilopascal. Just similar to that, that's if the Mach number is less than 0.33, we can consider the flow as incompressible. Similarly here, at two different locations, the pressures are given, and it is given that the flow is taking place isothermally. Now you have to justify that whether the flow is incompressible or compressible by knowing the pressure at two different locations. So now first, if we find the pressure at section 1 in terms of absolute scale, you know that the gauge pressure is in terms of the local atmospheric pressure. So just convert the gauge pressure to the absolute pressure. This is the gauge pressure plus the local atmospheric pressure. This is 109 kilopascal absolute. Similarly, pressure at another section, this is 5 kilopascal, so it comes as the 106 kilopascal absolute. So you know that for isothermal conditions, the density can be related to in terms of pressure since the temperature remains constant. So ρ2 by ρ1 you can simply express as equals to P2 by P1. So now our objective to find the density change between two locations. So if we find the percentage change in density between two locations, so ρ1 minus ρ2 by ρ1, that comes as 2.75%. So as the problem statement is already given, that the fluid can be considered as incompressible if the density of the fluid changes by less than 5%. So for this problem, since the density changes is 2.75%, so we can simply consider the flow as incompressible. So that means by knowing the pressure at two different locations also we can find, also without knowing the bulk modulus of elasticity, whether the flow is incompressible or compressible. Any questions?